This lesson is on work, and in a physics sense, work has a specific definition that's different than the way that you would use work in everyday life. So work in physics is not the job you have or how hard you're working. It is something very specific and different than those. In fact, work has two different definitions, and I'm going to give you both of them in this lesson. So let's start with the first one. In the first one, work is proportional to the force that's applied. So if an object has work done on it, or you're doing work to an object, part of that equation is that the bigger the force, the bigger the work. Secondly, the work is proportional to the distance over which the force acts. Again, the bigger the distance, the more work done. So if you combine these two ideas together, you get this one equation: work is equal to force times displacement. Now, there are a couple things you have to keep in mind when using this equation. The first thing you have to keep in mind is what d you use for the displacement. So here's an example. I've got this little boy who's going to push a car. And he pushes the car for a distance and then he lets go and the car keeps moving. The question I have for you is, what d do you use in that equation? Work equals force times displacement. Do you use the small one, the second one, or the third one? And I'm going to ask you to answer that in the Google form. If you need to see the animation again, just watch the video all over again. The second thing you need to keep in mind when using this equation is that the force on the object must be parallel to the direction the object moves. Let me give you another example. Here is little Johnny being pushed off to school, and when Johnny gets pushed off to school, Mom is kind of pushing him down at an angle. Like that. That would be the force vector involved here. Now, if this condition is true, and it is, we have to think about how it gets met. So the force that is important here is the force that is parallel to the direction he moves. Johnny is moving down the sidewalk. He's moving this way. And so the force that counts has to be this force. I only take a portion of this force, just one component of the force that Mom is pushing with. The other component of the force, the vertical component, doesn't matter. So I can ignore that in the equation, work equals force times displacement. The second definition of work is that it's a change in energy. And both equations work, or both definitions work. So if we look at another example here, here's a man who's doing some pull-ups. As he does those pull-ups, he's changing his own energy. So he's doing work on himself. The potential energy goes from small potential energy to big potential energy, from a low spot to a high spot. So the work is that change in energy. And it's the same exact numbers as the force times the displacement. So the numbers agree, it's just that you use one type of definition in one situation and another type of definition in another situation. Here's another situation, similar definition but a different situation. Now this car is moving. So the car moves from low kinetic energy to high kinetic energy. And as it moves there, it gets faster and faster, and the work done then is the change in energy again. So this time it's the change in kinetic energy that's the work done. Now, both of these definitions will be used, and you're going to most often use the second one, where work is the change in energy. Anytime the energy is changed, work is done by the object or to the object, and you just look at its change in kinetic energy or potential energy, or the change in both types of energy to figure out how much work is done.